Hello, my name is Chris Hartman, and I'm the Education Program Manager for MathCAD here at PTC. And on behalf of everyone in the MathCAD Business Unit, I'm happy to welcome you to today's first hands-on workshop. Now, I'm going to lead you through a brief introduction to engineering documentation for young engineers. In the history of product development, we know the great artists, designers, scientists, and engineers through the notebooks they kept to record their engineering design processes. Inspecting the sketches, analyses, and design criteria recorded in these notebooks provides us with both insight and inspiration. We are able to understand Leonardo da Vinci's genius more fully through the incredible machines drawn in his design notebook. We can see Edison's light bulb take shape in his sketches and his patent applications. We are able to read Alexander Graham Bell's notes from the development of the landline telephone. And in today's world, we are even able to learn more about Dean Kamen through the images from his engineering design process that are available on the internet. On a day-to-day basis, NASA engineers work to solve incredibly challenging engineering problems. Working in teams over years and even decades, NASA engineers perform many mission-critical engineering calculations. These images taken from NASA engineering documents illustrate some of the engineering calculations that an engineer might undertake on a NASA mission. Because its missions are expensive and dangerous, NASA engineers build rigorous design and review processes into every project. Nonetheless, NASA engineers, like engineers in all fields, sometimes make mistakes. When a NASA engineer makes a mistake, it can be very costly. The Mars Polar Lander was a 290-kilogram robotic spacecraft launched by NASA on January 3rd of 1999. The mission of the Mars Polar Lander program was to study the soil and the climate of Mars. 11 months after launch, on December 3rd, 1999, the lander descended from orbit to land on the red planet. During the descent, something went very wrong. Mars Polar Lander failed to reestablish communication with Earth after landing. The mission was over. Later, a NASA inquiry determined that the most likely cause of the mission's failure was a simple, yet catastrophic error in an engineering calculation. Furthermore, the error was not identified during the design process because of faulty documentation on the part of one of the design teams. As a result of this error during the design process, the spacecraft's engines ceased firing too early in its descent from orbit. This mistake caused the lander to impact Mars at a high velocity, 11 times the landing speed it was designed to achieve. After the post-accident inquiry, which determined that a multi-million-dollar spacecraft was lost due to a mistake in engineering calculation, Dr. Edward Wheeler of NASA stated, "People sometimes make errors. The problem here was not the error. It was the failure of NASA's systems engineering and the checks and balances in the process to detect the error. That's why we lost the spacecraft." The error that no one detected? One engineering team was using British standard units, while another engineering team was using metric units. Now let's look at an example of an engineering calculation. We'll use MathCAD so that we can demonstrate how its whiteboard interface makes it easy to perform the types of calculations you will face in the engineering design process. At first glance, a MathCAD worksheet looks very much like a word processing document. Yet, looks can be deceiving. In MathCAD, engineers can combine text, live mathematics, graphics, tables, and images to carefully document their work. You may be familiar with the engineering calculation presented in this particular worksheet. Isaac Newton first determined the equation for the physics of a projectile launched in the air. This worksheet employs Newton's equations to calculate both the maximum height obtained by the projectile and the length of time before the projectile returns to the ground. Let's take a tour of the worksheet to introduce you to the MathCAD regions you will learn how to use in today's workshop. A MathCAD document can contain text regions, like given measurements, and calculating the duration of the flight. MathCAD worksheets also offer mathematical regions, like the assignment of the initial velocity to the variable v0, the definition of the function height, and the evaluation of Newton's gravitational constant g, a predefined constant in MathCAD. As you can see, each of these statements uses standard mathematical notation. Finally, we see a graph on this worksheet. The graph plots the relationship between the function height and the variable t, with t defined from 0 to 5 seconds. The graph is a live mathematical object that is linked to both the variable t and the function height. As you look over this worksheet, you may have noticed that all of the numerical values have units attached, like 10 meters, 20 meters per second, and 9.807 meters per second squared. For many engineers and engineering students, MathCAD's unit capabilities are the #1 reason they choose to use it for their engineering calculations. MathCAD allows you to attach units to quantities, and it performs unit conversions automatically. For example, currently I have the maximum height reported in meters. If I want to see that height in feet, all I need to do is delete the unit meters and attach the units feet, and MathCAD will convert the result automatically. Now for a quick demo of MathCAD's linked live mathematics capabilities. In this worksheet, the quadratic formula is used to determine the duration of the projectile's flight in seconds. If we were to increase the initial velocity of the projectile, we would expect the flight time to increase. So let's try it. If I go up here, I can edit this value and change it from 20 meters per second to 100 feet per second. And now when I click outside of that region, the entire worksheet updates simultaneously. I have a new maximum height, still in feet. I have a time until the end of flight, and you can see how the plot has changed. Here was the original maximum height. Here is the new maximum. I hope that you have enjoyed this brief introduction to the role of documentation in the engineering design process and to PTC's MathCAD product. In order to make sure that your team has the best tools in its shop this season, PTC is proud to be able to offer them free copies of its best-in-class engineering notebook, MathCAD Prime. The following hands-on workshop exercises will help you to learn how to use MathCAD. We hope that MathCAD will help you and your team to achieve its goals in this year's competition. Thank you for attending today's workshop, and good luck.